Joel graduated in food and cosmetic process engineering, followed by a PhD in soft matters. And since 5 years, she works at L'Oreal in the analytical department dedicated to polymers and solids characterization. Her talk is about mineral pigment surface properties. And with this, I would like to hand over to you, Joel.
Great. Hello, everyone. Thank you, Ralph, and thank you to the organization team. You're doing an amazing job in preparation and also during this very interesting session here. Thank you to the previous speakers. I'm glad to share with you this study, and actually it's just the start. We've been working with Eric Brandley from AdScientist for the past 2 years in the analysis department in L'Oreal Advanced Research. And here, so I will introduce one of the application of IGC in our company, in our research center. And it's on mineral pigment surface properties, and mainly on the construction of a database, a knowledge database on mineral pigments. So my talk will be really focused on this construction of this knowledge database, but first I will introduce about how we use mineral pigments in cosmetic formulation and why we study, and we decided to do a proof of concept of the use of IGC to help formulators. Cosmetic industry uses a lot of pigments, not as much as other industries, but in fact, it's one of the main ingredients for makeup, for example, but not only. And apart from the main benefit of the color, there's also some specific benefits that we're looking for in terms of sensoriality as well. And the main mineral pigments used are iron oxides, titanium dioxides, and we use them in combination to create the perfect shade for the consumer. But sometimes we have to mix together with organic pigments, which have very different physical-chemical properties. We have different and various range of formulation architecture, and all these pigments has to be well dispersed in all these different formulation architectures. What is the main challenge of formulating pigments? In fact, apart from the color properties that are really the main end benefit of pigments, we have to fulfill a lot of criteria. We have to maintain the good formulation stability. We don't want any grains, we don't want any defacing. And also, as I was saying before, sensoriality is very important. And in fact, depending on the pigment and depending on the shade, you can have different textures, different rheologies. So we have to consider many parameters. And so the formulator, in order to make sure he has a good dispersion, he can select different oils with different polarity, but he can also work on the pigment itself and on the surface treatment, for example, of this pigment, to ensure a good compatibility between the dispersion medium and the surface treatment. So we have many manufacturers that are specialists into surface treatment. So they can offer different chemistry of surface treatments. So they offer hydrophilic, hydrophobic pigments. But one of the questions is actually how we can select between two different hydrophobic pigments, for example. So the manufacturer described their technology by the chemistry, by a generic term that everybody knows, the hydrophobicity, hydrophilicity, and also they bring some examples of formulation, as you can see on the right picture here. Example of formulation, just the aspect, for example, of a formulation with no treatment and with a treatment. So a pigment, no treated, non-treated, and treated. So it's interesting, but as you can guess, it's time consuming. We have to perform this type of evaluation in all types of formulation architecture. So that would be great if we could have intrinsic parameters, intrinsic properties of this raw material, and it can be used for any formulation architecture. And of course, it could help to create functional specification to explain what we are looking for and to find alternatives, for example, like for natural or natural-based ingredients, also different sourcing of raw materials. But today, well, not today, but from ever, how do we describe the pigments? So you can see on the right-hand side a TEM image of yellow iron oxide here. It's a needle shape. So we can describe the physical characteristics, the morphology, the primary particle size, the specific surface area, and the density related to the chemistry, as well as the bulk or tap density, which is very important for formulators. But what is important as well in terms of formulation, and that's all about the symposium today, is about the surface properties. All these terms you can see here, there are methods actually, but which one is the most appropriate to differentiate, to distinguish between two types of coating, for example. So here is a list of techniques that everybody knows, methods, that some are conventional to describe the surface property of powders. As we know, powders are multi-parametric, which is quite difficult to approach. And we thought that IGC could be very interesting for the fact that there is little sample preparation, and it gives access to a very wide range of physical-chemical properties. But in our company, it's not conventional. So we proposed to do a proof of concept because we didn't have any reference data on pigments and on coated pigments. I'm not talking about the surface energy of plates or whatever. This is okay. But on single particles, we couldn't have any reference data. So this is why we started working with Eric. And I will not explain everything about this because people have already detailed. But we follow the proposition of the expert, and so the first thing from our side, we selected a set of 30 samples, so which are iron oxides and TiO2 from different suppliers. They have different morphologies, as you can see on the image here. They have different coatings: hydrophilic, hydrophobic, lipophobic. And we did a reproducibility test, little one, but at least, and one batch variation as well to comfort us in the study of this data. Our scientists selected a single protocol for all these samples according to their experience. So first thing, the reproducibility test was done over 2 analyses over 3 months, just to check if, in fact, we had close results. And it was made on a yellow iron oxide with no treatment, so we call it native. And all the parameters you can see here are the ones that were described in the previous talks. And the range, you can check, the range that I plot here is actually the range of all the 30 samples that you will see later on. So it's just an overview to see if we can really, if there's a close relation between, I mean, if we have close results between the 2 analyses, which was the case. We were convinced to continue. Second thing was the batch variation. So 1 red iron oxide native, we have 3 batches. And again, we were quite confident that we had very low batch variation. So it comforted us into going on into this set of 30 samples. So now comes really the database, the start of the database, and we have 4 categories of treatments or surface. We have the native, we have hydrophobic treatment, which is silicone, amino acid, or stearic acid. We have hydrophilic treatment, phytic acid, silica, alumina, and also 1 fluorinated TiO2, which is lipophobic treated. So the 2 axes are, so the y-axis is the dispersive surface energy, which is the apolar part of the surface energy. And on the x-axis is the nano-roughness index. It's actually the inverse of the morphology index. I thought it was easier to say when the nano-roughness index is high, it means the surface is rough. There was just an easier way to have this in mind. So when we plot this, all the 30 samples we have, so you can see the black iron oxide, the red and the yellow, and the gray is the titanium dioxide. We actually have a very wide range of surface energy. So as Stephen Abbott said, there's a we can we can think is 200 nanometer per meter, is millinewton per meter, sorry, is really realistic. Actually, we can see it's really rough. It's probably the fact that the sample is actually rough on the surface. So we have a very wide range, and we have some outcomer, or how you say, like the fluorinated sample here, and the yellow, one of the yellow native iron oxide. What is very interesting is to check all the native samples, pigments, are very scattered in the range of dispersive energy and nano roughness, while the hydrophobic are very all gathered together and on the low surface energy, which was expected, and also on the low roughness. So again, that was expected. We were happy to see that it was actually the case. And hydrophilic samples are in the middle, and they are a bit gathered, but still have quite high surface energy and quite high nano roughness index. And the fluorinated sample is really, really peculiar. We knew that. In formulation, it's really, really specific. It's probably very difficult to replace. If we focus on the low dispersive surface energy, on the hydrophobic here, if we zoom in, we can actually see interesting differences here, especially for the amino acid. These samples are actually coated from the same supplier, but not from the same origin. It's not the same mineral origin. So we see that we have similar surface energy, but different nano roughness index, and we have similar specific polar interactions. We could ask ourselves, could we talk about surface heterogeneity? This probably we should go into finite concentration to check about this point. The last representation I will share is the one that was shared before by Eric and Stephen. It's the different domains that we can check in terms of the hard and nano-rough surface here, the mixed and hard and soft surface on the green part, and also the soft domain. And when we plot what the database, the 30 samples, we see that all the hydrophobic samples are in the soft domain, so which is really clear. This is what we were expecting. And, but actually we can make differences between these samples. This is what is interesting for us. So finally, I will end this talk by saying that IGC, the proof of concept is quite interesting, and we need to go further now into the relation between the functional properties in order to gain more knowledge and to predict the dispersion, and of course to be able to compare two pigments, two coatings, two technologies to make sure one can replace another or one is better than the other. So this technique could quantitatively distinguish different coatings. We have two questions remaining. In fact, in the formulation, we mill, we grind the samples, and this part was not studied here. And we have to consider what happens when milling or grinding. And again, one of the challenge in the quality of the coating is the homogeneity of this coating. And I think here we did not address that. And probably we should talk to Eric or to Stephen to think about finite concentration to check if we have, if we can compare homogeneity of coatings from different sources of coating technologies. Thank you for your attention, for your interest, and I'm here for any questions.